Okay, now we get to make some interesting shapes with our hands, which is everybody's favorite part, or the invigilator's favorite part of the exam, is when the students start getting to the magnetic field questions and they will start, getting their left hand rules out or their right hand thumb rule. I said that the magnetic flux density is defined as the force per unit length, per unit current on a wire. So it's almost as if instead of a charged particle, charged test positive particle, the magnetic equivalent is like a little stretch of current carrying wire. So that seems like a good place to start. What's the magnetic field around a wire? It's concentric circles, and they go round in loops. Which direction do the loops go? Well, that's where we introduce our right hand grip rule. If the current is flowing this direction, you get your right hand, stick in the air as if you're doing a thumbs up, point your thumb in the direction of the current, and the way your fingers curl around the wire, that's the direction the magnetic field will be flowing. This field itself then dies off the further you get from the wire. That makes sense. Okay, so this is the direction the current is flowing. Just a reminder from yesterday, that means the electrons are actually moving down towards this end of my wire. And it's the movement of those charged particles which causes the magnetic field. Okie dokie. What happens then if, instead of considering that about the magnetic field that a wire generates, what happens if I put a wire in a magnetic field? So instead of what happens is a magnetic force acts on our wire. The next question is, what direction does that force act in? And for that, we need our Fleming's left hand rule. Okay, so a current carrying wire in a magnetic field causes a magnetic force to act on the moving electrons in the wire. Why does this occur? So let's say the current is flowing left to right, therefore my electrons are all moving right to left. Okie dokie. In the field, let's say it is moving into the page. Is everybody happy if I use this notation? It's standard notation, you do need to know it. If you see this symbol, it means the field is going into the page on which it's written. And if you see this circle in the center, like an arrowhead that's coming at you, this means the field is coming out of the page. Okay, how do we determine which way the force is acting? We align our first finger, our index finger. F is for field. Our second finger, our middle finger, so it's second, it has a C in it. We align that with the current. Bear in mind, that is the current we are aligning with, not the movement of the electrons. And the thumb will therefore point the correct direction. Thumb has an M, so that's where the motion is. Or alternatively, you can just say, look, it's a flagpole. That's where the force comes in. Whatever mnemonic works for you, as long as you've got field, current, and force. Right, so let's apply it to our little wire. If the field is going into the page, the current is going left to right, you can then see the force, the resulting force on this wire, is going to be acting up. What is that force caused by? Well, it's because there's a force on all the electrons. And all the electrons want to move that direction too. And so they will carry the wire with them. Okay. So 2 hand rules to be handy with. The right-hand grip rule for the direction of the magnetic field lines around a wire. And then Fleming's left-hand rule, what direction is my wire going to move if I put a current carrying wire in the path of a pre-existing magnetic field? The strength of the magnetic force, measured in magnetic flux density, depends on the magnetic flux density in Teslas, the current in the wire, and the length of the wire. We said, when we defined the magnetic flux density, we said it was the force per length per current. You can rearrange this to say that the force on a wire, the force whose direction we worked out on the last page, what's the strength of that force? It is the magnetic flux density times the current times the length. The only other factor we need to add to that is that the force is at a maximum when the wire is perpendicular to the field. That was also, if you remember, I can't go back that many slides, but if you remember when we defined magnetic flux density, we said it was the force on per length per unit current on a perpendicular wire. So if it's not perpendicular, say the angle between the wire and the field is theta, so we then need to add a sine theta. Why sine rather than cos? It's because we've said the maximum force, the force is at a maximum when it's perpendicular, i.e. theta is 90. Which of our trigonometric functions is at a maximum when theta is 90? It's sine, not cosine. And it's more convenient to be able to draw our angle if we just say, look, it's the angle between these two things, rather than it's the angle between the normal to the field and the wire, which, yeah. Okie dokie. Very good. So that's the situation if we have the field is acting from left to right. The current, if the current was flowing that direction from here to here, that means the force would then be acting downwards if you apply your Fleming's left-hand rule. That would be acting downwards with BIL, Bill, my mate Bill, sine theta. Okay, let's try an exam question on that exact thing. Consider a straight wire of mass 6.5 grams passing through a magnetic field, magnetic flux density they give us. 14 centimeter of the wire is exposed in the field. And it's perpendicular to it, so we can actually just simplify this to F equals BIL. The diagram shows the setup of the wire and the magnetic field. As an electric current passes the wire, it moves with a constant acceleration. Constant acceleration, that implies a constant force because they are directly proportional to each other with Newton's second law. And acceleration they give us into the page. Nice. Calculate the strength of the current flowing through the wire and state its direction. Interesting. Okay, yep, so we've got acceleration into the page, got the mass. If they give us the mass and the acceleration, I'm already thinking, well, look, we can work out the force. If we can work out the force, we're given the length. We are given B, and then work out the current. We need to calculate the strength of the current and its direction. The direction, we can hopefully work out now. We know the force is acting into the page, so we need to align our thumb into the page, which is a slightly awkward motion. Which way are the field lines flowing? Well, they always flow from north to south. So I need to align my first finger with the fields. So already I'm doing this sort of strange motion. Thumb, dead ahead, field over here. Where's the current pointing? It's pointing down. So the current will be flowing from the top to the bottom. Right, determine the force acting on the wire. Yep, F equals ma. Multiply your mass. Bear in mind that they gave it in grams. So we need to multiply 10 to the minus 3. Determine the current in the wire. F equals Bill. Rearrange to get I is F over BL. Plug in your numbers, you get 1.24 amps. Is that crazy? No, it's not. Something on the scale of amps or milliamps is, more or less normal. If the acceleration goes into the page, the force goes into the page, use your left-hand rule. The current must be going down on the page. I actually think that was a pretty friendly 5-mark question. You basically get 2 marks for knowing which way fields flow and using your left-hand rule. So